When environmental conditions become unstable, shelter stops being a static structure and becomes an active system that must regulate heat, airflow, moisture, and structural integrity. Survival is no longer determined by the presence of walls and a roof, but by how effectively a space can maintain internal stability against external stress. The transition from stability to danger does not begin with obvious destruction, but with subtle shifts, small drafts, uneven temperatures, and gradual exposure that disrupt the body's equilibrium. Within a short time, these changes can lead to dehydration, hypothermia, or heat stress, depending on the environment. A major reason shelters fail under real conditions is the misunderstanding of what shelter actually provides. Being indoors does not guarantee protection. Modern buildings are designed for comfort during stable conditions and rely on active systems such as heating and cooling. When these systems stop functioning, the building's passive characteristics determine whether it remains habitable. A structure can remain physically intact yet become thermally unsafe. Large open spaces lose heat quickly. Thin walls allow rapid temperature transfer, and windows become major points of energy exchange. As a result, indoor conditions can begin to mirror or even worsen external extremes. The core factor in shelter survival is heat transfer. Maintaining thermal equilibrium is essential for the human body, and this becomes difficult when the environment cannot regulate temperature effectively. Two physical properties govern this process: thermal mass and insulation. Thermal mass allows materials to absorb and store heat, while insulation slows the movement of heat between environments. These properties must work together. Thermal mass alone cannot retain heat without insulation, and insulation alone cannot stabilize temperature without stored energy. When properly balanced, they create a buffer that slows environmental change and improves survivability. One of the most important and often counterintuitive findings is that smaller spaces are more effective for survival than larger ones. In the absence of external energy sources, the human body becomes the primary source of heat. Smaller enclosed areas retain this heat more efficiently, reduce exposure to drafts, and require less energy to maintain livable conditions. Large spaces, by contrast, increase heat loss and accelerate fatigue. Consolidating into a smaller, controlled space can significantly improve the chances of maintaining thermal stability over time. Airflow introduces another layer of complexity. Moving air increases heat loss through convection, even when temperatures are not extremely low. Drafts caused by gaps, broken windows, or pressure differences can continuously pull warm air away and replace it with colder air. This process is often subtle, but highly effective at lowering body temperature. However, completely sealing a space is not a viable solution. Without ventilation, oxygen levels decrease and carbon dioxide accumulates, leading to fatigue, impaired thinking, and reduced decision-making ability. The challenge is to strike a balance by minimizing uncontrolled airflow while maintaining small, controlled openings for necessary air exchange. Positioning within a structure also has a measurable impact on survival. Lower levels tend to be more stable because they are less exposed to wind and benefit from insulation provided by surrounding materials or the ground. Upper levels are more vulnerable to environmental extremes. Interior rooms, especially those without direct exposure to external walls, provide additional buffering against temperature fluctuations. Choosing the right location within a building can significantly reduce exposure and improve overall conditions. Moisture is a less visible but equally critical factor. Everyday human activity, breathing, sweating, and cooking introduces moisture into the air. Confined spaces, humidity levels can rise quickly. This has direct consequences for thermal regulation. In cold environments, moist air increases heat loss because it conducts heat more effectively. In hot environments, high humidity interferes with the body's ability to cool itself through sweating. Moisture also contributes to mold growth, material degradation, and reduced insulation performance. Managing humidity requires controlled ventilation and careful use of materials that limit condensation without trapping moisture inside the living space. Over time, even small imbalances in heat, airflow, and moisture can lead to a gradual decline in shelter conditions. This deterioration is often not immediately noticeable, but becomes significant as it accumulates. Damp materials, rising humidity, and decreasing insulation effectiveness all contribute to a weakening of the shelter's ability to protect its occupants. Survival is therefore not just about immediate protection, but about maintaining Over time, even small imbalances in heat, airflow, and moisture can lead to a gradual decline in shelter conditions. This deterioration is often not immediately noticeable, but becomes significant as it accumulates. Damp materials, rising humidity, and decreasing insulation effectiveness all contribute to a weakening of the shelter's ability to protect its occupants. Survival is therefore not just about immediate protection, but about maintaining conditions over extended periods. As environmental stress increases, structural integrity becomes a growing concern. Buildings are designed to handle specific loads, and when those limits are exceeded, weaknesses begin to appear. Cracks form, supports weaken, and materials degrade. These failures are often incremental rather than sudden. Partial damage can be especially dangerous because it alters the behavior of the structure while still appearing usable. A damaged roof may allow water to enter, increasing moisture and reducing insulation, while weakened walls may introduce drafts and instability. An important concept in structural behavior is load redistribution. When one component fails, the load it carried is transferred to other parts of the structure. If those parts are already under stress, this can trigger a chain reaction of failures. Early warning signs, such as unusual noises, visible cracks, or shifting materials, often appear before major structural collapse. Recognizing these signs provides an opportunity to take action before conditions become critical. As conditions worsen, occupants face a difficult and ongoing decision, whether to remain in a compromised shelter or leave and face external exposure. Staying may mean dealing with declining internal conditions and increasing structural risks, while leaving introduces immediate environmental dangers. This decision is not fixed and must be continuously reassessed as conditions evolve. Ultimately, shelter under extreme conditions must be treated as a dynamic system rather than a static refuge. Heat, airflow, moisture, and structural stability are interconnected variables that must be actively managed. Changes in one factor inevitably affect the others. Sealing a space may improve heat retention but increase humidity. Increasing ventilation may reduce moisture but also increase heat loss. Survival depends on understanding and balancing these competing forces. The key insight is that effective shelter is not defined by its materials alone, but by how those materials are used and managed under stress. Smaller, well-controlled environments outperform larger, unmanaged ones. Airflow must be regulated, not eliminated. Moisture must be controlled alongside temperature. Structural integrity must be monitored continuously. In unstable conditions, precision and adaptation, not comfort, determine whether a shelter sustains life or accelerates decline.